Hey guys, it's OC here for another guided notes session for you. There's been some questions about atomic theory, and a lot of you probably don't know a ton about atomic theory, and if you do, this is probably useful for a review for you. So let's take a look at some basic atomic theory concepts. This won't delve into everything, but it'll get you kind of the basics, okay? The atom, that's like the smallest part of matter, essentially, what we say. Not that there's anything smaller than an atom, but our basic definition is it's the smallest unit of an element that it can exist and have its certain physical and chemical properties. Atoms are the fundamental basis of everything. This pen, this mouse, my coffee. Everything is fundamental atoms. Even compounds have atoms in them. And the whole idea of the atom was started by this guy, John Dalton. All right, he's dead. He's way dead. But John Dalton is kind of the father of atomic theory, and there's a great picture of him right there. Look, he's just amazing. A picture like that, you could tell that's a cell phone picture. That's the new iPhone 5's picture, capability. That's an Instagram filter. Anyway, so John Dalton, he kind of did some experimentation, and he came up with some basic theories. Depending what book you read, there could be 5 theories, 6 theories, 4, 3, 1. Some of his theories were incorrect, but there are kind of basic theories that hold true even to today. Okay, for instance, atoms of one element are exactly alike. Okay, but different than atoms of other elements. So his idea was, listen, you have an atom like A. Okay, or this could be gold. Let's say this is a gold atom. Okay, and since it's a gold atom, maybe it is gold itself. Okay. Whereas you might have another atom, like iodine, and let's make iodine really big, okay? And iodine atoms are way different. It's bigger, different color, because back then he didn't really have you can't see the atom. So since you can't see the atom, these were kind of deductions you make based off of macroscopic, hey, I see that this is white, so maybe the atoms of it are white, and that's a good start, I think. But he would say, okay, well, if you have this iodine, I've seen other iodines, and all iodines must look almost identical to each other, okay? Just like all these golds are going to be smaller, but all the golds themselves will be the same color, okay? And have the same properties and everything like that, okay? Now, that's not absolutely true anymore. He's still got the basic premise correctly. Or, we'll learn about isotopes in a little bit that make these atoms a little different even from themselves. So, like, not all gold atoms are exactly alike. And not all iodine atoms are exactly alike, okay? But they are pretty darn close. So John Dalton really ain't too far off, okay? Atoms tend to rearrange themselves in chemical reactions, okay? But they aren't destroyed or created. This leads us to a law that Antoine Lavoisier proves for us, the law of conservation of mass. Okay? All right? Law of conservation. Whenever you talk about the law of conservation of anything, conservation means keeping, not destroying or creating. And mass, sometimes you might hear this referred to as matter. Sorry, it's not supposed to be a little abbreviation there. Wrong one. But the mass means that atoms can't be created nor destroyed. You just can't make them. You can't create. You can't destroy them either, which is still pretty fundamental. That's still relatively. I mean, it's a law. The law is extended a little bit now, but that's still a basic law that we can work with. So, for instance, if I take these gold atoms and react them with iodine atoms, then I make gold iodide, let's say. Then I'll take a gold atom and maybe it combines with an iodine atom, okay, to make gold iodide, okay? But you can see that one atom of gold, and here I'll even color it for you, one atom of gold combines with one atom of iodine and makes gold iodide. No atoms are created, no atoms are destroyed. This must have come from one of these gold atoms and one of these iodine atoms, okay? So that's Antoine Lavoisier, all right? And if this were to break apart, if you were to destroy this, well, you'd get a gold atom out of it, and you get an iodine atom out of it. All right? Law of conservation of mass. All right? That you can't create nor destroy atoms. Okay, they can rearrange, they can combine, they can split apart, they can, 3 of these can go with 4 of these, and 22 of these can go with 6 of them, and 8 of these, things like that. But they don't get created, nor do they get destroyed. Okay, now you're going to find out a little bit that we can expand that a little bit. Einstein kind of goes a little bit into more of that. Okay, all right, and then 3 kind of follows that idea. All right, that compounds are just combinations of atoms. Okay, so that's John Dalton, father of atomic theory. All right. After that, the 2 most notable scientists, the next one really is J.J. Thompson. J.J. Thompson is this guy. This is J.J. right here. Good old J.J. All right, as they call him back in high school. They were like, J.J., yo, J.J., what's going on, J.J.? I wonder if he went by J squared or 2J or 2J. Anyway, this guy discovers one of the first subatomic particles, and he discovers the electron. All right, and you might say, well, how does he discover the electron? There's some other people that do some studies before then that figure out that there are these charged kind of particles around, these charged ability to charge things. Let's not worry about any of that. But the basic idea here is that William Crookes developed this thing called a Crookes tube, in which on one side of the tube there's this thing called a cathode and this thing called an anode. Okay, and that was discovered. And what we knew is when you put a large voltage across this, when you put a huge voltage across this into a vacuum kind of area here, you ended up getting this beam of light across like you see a zinc sulfide screen, like glow in the dark. It's glow in the dark, okay? And what's cool is when you did that, this little screen would glow. A beam of light would make it glow. So you're like, oh, that's a ray. So he called it a cathode ray, okay? So sometimes you hear this referred to as a CRT, cathode ray tube. That's the big fundamental thing behind those really big old TVs, monitors on computers that are the real big ones, not the LCDs that are really thin, but the big ones that are big and thick and deep, okay? So that's the CRT. Now, why did we know that was electron? Well, we didn't, okay? First thing J.J. Thompson did was, well, he said, okay, well, if I apply a positive and negative voltage to 2 plates, on parallel to this line, this beam, then if it's a ray, then there's no effect to rays and charges. I could put these 2 plates right here, and that doesn't bend the light away from me. I don't see blackness or something like that. By the way, you don't see blackness. I just don't see nothing. I don't bend light that way, okay? Bending light occurs by refraction or diffraction. That's not done by charges. Well, and the cool thing is, look, it actually did, go up towards the positive side. So that told us that this beam, since it goes up towards the positive and away from the negative, since similar charges repel and dissimilar, different charges, attract, that told us that this beam was negatively charged. Okay. Now there's another video I have up online called the railway tube, and what he did there was he put like a 2 kind of rails in here, and then he put like a pinwheel, okay, like a water wheel thing, okay. And that and the idea was, if it's a ray and you shoot this beam at this, if it's a beam of light, beams of light are energy and don't have mass. Okay? If it's a particle, it has a mass. Beams of light don't have mass. We already have an idea that this probably isn't a beam of light because it's got a charge. So to him, well, if I put this in here and it has mass, it'll spin the wheel. The wheel will spin, like a wheel and go roll down the little thing. And that's what it did. It did. He turned it on, it goes, and this wheel goes, whee! Okay? And then because of electricity, you can reverse the charges. You can turn this into the cathode by just flipping a switch, and turning this into the anode, changing the charges that they are, anode, gotta spell anode. And then he could make it go backwards. Okay? So that told us that it was negatively charged and it has a mass. Okay? So he discovers the electron, E minus. Okay? Superscript. Remember, superscripts tell you charges, subscripts tell you a number of things. Okay? So the electron. He knew that the electron had a really low mass, but a really high charge. He actually discovers technically the charge to mass ratio. Later on, this guy Millikan finds out a little bit more about the exact Coulombic charge on it, and then you can find the mass of the electron. But he knew it was really small. Okay, so that's J.J. Thompson. Okay, J.J. Thompson, later on after this, comes Ernest Rutherford. All right? Ernest Rutherford is really, really fundamental. Okay? In fact, probably what you know now comes from Ernest Rutherford. All right? Ernest Rutherford is very famous for this experiment called the gold foil. No, he didn't go steal foil. And no, he wasn't like, well, you know, everybody else uses aluminum foil to package their lunch food, so I'm going to use gold because I'm just that snooty. No, he didn't do that. Here was his idea. He noticed that gold foil is really cool. Gold foil, when you pound it out, when we had the technology to actually go bam, 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 and malleable, because it's malleability, to thin it out, it became translucent. Whoa! Solid. A solid becomes see-through. And that's kind of cool. Something that wasn't see-through is suddenly see-through. So that kind of gave the idea that maybe the atoms that make up gold are not like discretely like solid spheres like kind of Dalton was thinking. You know, at this point with J.J. Thompson and Dalton, we'd say there's solid spheres and there's negative charges inside of there. And we would agree that there were positive charges. In fact, the model that they talk about is the plum pudding model, where these like little plum pieces of negative charge, you know, are in this little sphere, and I'm not going to draw all the circles, and it's in a sphere of positively goop. Okay, kind of weird how we came up with that idea. I call it the chocolate chip cookie dough. Like our little negative electrons are our chocolate chips, and the positive dough holds it all together. Okay. Anyway, so what Ernest Rutherford was thinking was, well, maybe there's a whole bunch of space. Okay, maybe there's just nothing here, and that can allow light to get through. Okay, because that would be one of the explanations how a solid can be pounded out and suddenly get thin enough that you can see through it. Okay, so here's what's the setup. Again, glow in the dark screen. So this is another glow in the dark screen, and he's going to fire alpha particles. Okay, I'll do a little thing on radiation in a little bit. But alpha particles have a positive charge. These were kind of discovered by Henry Becquerel, Marie, and Pierre Curie. Also did a lot of studies with radium to discover a lot of alpha particle stuff and radioactivity stuff. And so what he did is they put a source in here of radioactive particles. And these radioactive particles came out of this tube and shot down here and would hit the gold foil. Now, if Dalton's right, Dalton and J.J. Thompson, when matter hits other matter, it's going to go boing, boing. So all this should go boing, boing. All right? But if it's like kind of Ernest Rutherford was thinking, maybe some of these particles could go whee. All right? So when he actually set this screen up, and this thing was actually a lot more cumbersome. This screen was not like so as nice as you see it here. There's a video of a guy who shows you a modern interpretation experiment. Oh man, he really labored over this experiment for a long time. Ernest Rutherford did to actually make this work out, because back then he didn't have this huge screen. He had this like little thing that he would just sit there in a dark room going, oh, is it lighting up? Is it lighting up? Is it lighting up? And he would do that for hours in dark rooms, okay? So anyway, what happened was he found out that he got most his impacts, the screen would light up in this area. It lit up directly across from where the beam was shot from. Holy crap! That means if these positively charged particles get through here, they aren't bouncing off like Dalton or J.J. Thompson did. It must go way right through. Okay? Now, some of them you could see did deflect. He actually did notice that there was still some deflecting as they went through. So that told him that there must be something very small in the middle that is positively charged, because it's deflecting the positives away. That they're going wee away. Okay, remember, positives and positive, woo! Positive negatives, wee! Negative negatives, woo! Okay, so that told him that they must be positive. And by the way, what told him it must be small is that some particles, very few, did directly bounce back. So that would explain that some of them must have hit something or get really close to something, maybe that positive charge, and bounce back. Not many, but some. Okay, so that gave us this idea that there must be the center part of an atom that he termed a nucleus. Yeah, sort of like the cell, but not really. It's the center part of the atom, and it is positively charged. Okay? And most of the particles go right through. You know, you could see most of these particles go right through. Some will deflect, but still go through. Very few actually can hit that center. An analogy for this is, like if you had a football field, you know, which is 100 yards, 120-ish yards, if you include the end zones, 120 yards here, okay, that the nucleus on the middle of this makes up about a quarter. That's a quarter. That's a 25-cent piece. Okay, right there. That's the nucleus compared to the outer edges of the football field. Okay, that's the size of the nucleus. So a major conclusion of Rutherford's experiment, there's a center that's positively charged, and most of the atom is nothing. It's just empty space. You're mostly empty space, like 90-some% of you is just emptiness. To think that even this, that I can't see through, is emptiness. Empty space. Okay? And we start to figure out that this is where the electrons are, somewhere in here, but again, they're really tiny. Really tiny. Really tiny. Yeah, the nucleus and the protons that are inside of there, which are later found out, are found to be like 2,000 times bigger than that of an electron. But most of everything is empty space. Okay? Someone says that, you have nothing for brains. You're like, well, so do you. Ha! I see what I did there. Yeah. Okay. All right. So Rutherford, atoms are mostly empty space. Someone says, what's mostly in the atom? Nothing. Okay? And then if they ask what particles are in it, we'll get into that. But there's a center nucleus. And that holds true today. There's nothing changed about that idea. That this chocolate chip cookie dough model, bye-bye. Nuclear model, hello. Okay? All right? Not to get into their experiments. If you want to learn more about them, please look them up. Okay? But from later on experiments, James Chadwick, this guy right here, discovers a neutron, one of the last particles to actually figure out, okay? It is a neutral particle, which is about the same size as what Henry Moseley figures out, this guy down here, which is the proton, okay? So Henry Moseley figures out that there's a proton. These guys have about the same mass, but the proton has a positively charged charge to it. That's redundant. OC is redundant. That's a positively charged particle, about the same size as the neutron, but opposite in charge to the electron. So it's kind of cool. The electron, it has almost no mass comparative to the proton, but has an equal but opposite charge. Okay, all right. So that's kind of neat. And then this guy right here, that's Millikan. This is the guy who actually figures out the actual charge on an electron that allows us to discern the actual mass of an electron to be very, very infinitesimally small. Okay, so a lot of times when we say the electron has no mass, it's because these guys right here are so much bigger than than this electron is. So like we always say, the electron, even if you had 100 electrons, why do you care? Because one proton is still bigger, much bigger than it. Okay, so you should know these guys by name and what they discovered. Chadwick neutron, Moseley proton. Again, that gets to our atomic number. And Millikan, just know he does this thing called the oil drop experiment to figure out more things about the electron. Okay. Right. Okay, so that's kind of simple atomic theory. I hope this helped out. Gives you some basic understanding of that we believe in a nuclear model right now. That's what all of our experiments to this day have proven and seem to prove, and no contrariness to that at this moment. There's been some modifications how things are arranged inside the nucleus, but there is a nucleus. And there is that electron cloud, this mostly empty space that has electrons in it. Okay, there are neutrons, there are protons, and there are electrons. Okay, all right. So I hope this helped out. I hope this kind of solidified some understanding. Shoot me an email if you have more questions. You can find me at avogadrosg1@gmail.com or my school email address at oconpet@wcps.k12.md.us. For OC, I'll see you guys next time. Have a good one, all right?